So with Newton's law of gravitation, right, of universal gravitation, it generally describes the force of attraction between two masses, right? So let's say that we have mass 1 and we have mass 2, right? With between any two objects in the universe, that's why it's the universal gravitation law, right? There are some attractive forces. There will be a vector of a force, some of attraction that M1 is exerting on M2. So the red vector, right, speaks to the force M1 exerts on M2, and the green would be the force, my bad, that's white, and the green would be the force M2 exerts on M1, right? So any two masses, M1 or M2, right, separated, I forgot to add this, separated, right, by a distance r, we use r as the distance in this case, right, separated by a distance r, will have some amount of gravitational force associated with them, right? So we need to understand this, right? So firstly, what happened here? Newton realized that the forces between two masses should, one, right, be proportional to the product of their masses. Right? So the gravitational force, right? So the force should be proportional to the product of the masses, right? So what we're saying, right? If M1 or M2 were to increase, right? The forces in between them. So the force between them, or forces, I should actually note. Forces, right? Let's just use force. We're focusing on one force. Let's not make it too complicated. The force between them increases, right? So focusing on that first fact there. Fact two, right? It should be inversely proportional, right, to the square of the distance between them. It is a part of what we call the inverse square law. So I want you guys to look that up, the inverse square law, right? The inverse square law states that the distance r, so I wanted you guys to look it up, but because I'm so excited, I'm just going to state it here. It shows that distance r, let me just write it clearly, distance r, right, increases, or that when the distance r increases, right, the force decreases by a factor of r squared. That's always stating there. So I end up with something like that. The inverse square law. Alright? So are we okay so far? So we're looking at the two things that Newton stated, right? So we know that two objects that have mass will have some gravitational force associated with them. The first thing that we'll look at, right, is that it should be directly proportional to the product of the masses. And the second thing is that it should be inversely proportional to the square of the distance between them. Drop a 1 in the chat if everybody's okay. Are you guys good? Waiting for the responses. Are we okay? We're going to write it in the equation so you can see what I'm talking about if you don't see it already. Are you guys good? Not seeing any responses. Did anyone die? Are you guys okay? Okay, we're good. Okay, we're good. But we'll pause for a minute now. So like, are there any questions? Alright, so I'm pretty sure that if you guys have a question, then you'll probably just state it, alright? So let me change back to purple because my derivations should be in purple. I don't know why I haven't been doing them in purple. Alright, but let's move on. So what are we stating from these two things? When we combining the factors, right? Let's just use the word thus. Combining the factors, right? Combining the factors gives us, let's get this. We are saying that the force exerted, the gravitational force F subscript G, is directly proportional to the product of the masses m1 and m2, but inversely proportional to the square of the distance. Can you guys appreciate that? This should be good, right? Directly proportional to the product of the masses, but inversely proportional to the square of the distance, as we were stating, right? And in order to get rid of the proportionality sign alpha, we need to introduce a constant, right? Introducing the gravitational constant. Go ahead. Introducing the gravitational constant G, which is equal to what? What is G equal to? Nobody knows what G is equal to? Remember, G is equal to 6.674 times 10 to the negative 11th power Newton.
9.81.
Yeah,
Oh, no.
6.67481 squared per kilo. Let me not do that. Kilogram per kilogram.
Sir, what did sir? What, sir?
Mm-hmm.
Excuse me.
Mm-hmm.
Sir, isn't gravity 9.81?
Hold on there. Little g is 9.81. This is big G. Constants are different. Meters per second squared. This is, remember, that would be the acceleration due to gravity on Earth. But what we're looking at here is the universal
Okay.
gravitation. If you want to find little g, you can use gravitational constant in order to find little g. We can derive it if you want, right? But let's finish with this equation. So if we introduce a constant, right, a proportionality constant, we can reduce the equation to being Fg is equal to G m1 m2 all over r squared. That is how we find the gravitational force between two things. Alrighty, that is it. The next concept that is on the topic would be the gravitational field strength. So before we start that, are there any questions? Go ahead. Gravitational field strength is next, right? Alright, so you guys should be able to apply something like this. So let's say that we have a mass 1 which is 100 kilograms.
Sir,
Go ahead.
sir, what does the R represent again?
Distance. R represents the distance. So R is the distance between M1 and M2.
Um, what does R represent? Alright.
Alrighty. So we have that there. So the gravitational field strength that we're working with now, the gravitational field strength, it speaks to a point, right? We're talking about at a point, right? So gravitational field strength relates to a specific point. Alright? Let me write at some point. Because if we have a gravitational field, let's say that we have an object here and there's a gravitational field around the object, the field strength at this point A may be different to this point B. That's why I say at a point, right? So the gravitational field strength at a point now, right, is going to be, right, or is defined as, let me just write the definition, right? So it should be the gravitational force, right, per unit mass. All right. We can also say it's experienced by a small mass, or small test mass placed at a point. All right, but I'm just going to reduce it to that. All right. So what is it? Gravitational field strength G is equal to F over M, where G is the gravitational field strength, F here is the gravitational force that we calculated above, or that we can calculate from above, and M is the mass, right, of the object. So the mass of the object experiencing the force. All right. So that's that equation there. The unit of G now. All right. How do we get the unit of G? What would be the unit of G here? Anyone? We have force, right? Force would be newtons, which is over mass, which is kilogram. Therefore, it is Newton per kilogram, right? And let me just satisfy what Divine was alluding to earlier, right? So this is the gravitational field strength, right? So how do we get the Earth's surface, right? So like what's happening on the Earth's surface, right? So for example, at the Earth's surface, right? The gravitational field strength G speaks to what? The force
Sir,
experienced. Go ahead.
since the
Okay, give me a moment. So the gravitational field strength G, right, on Earth's surface would be relating to any object of a mass, right? So remember, it's mass over gravitational force, right? In our case, our gravitational force is actually 9.81, right, newtons, right? And the mass we're using is 1. Therefore, our acceleration due to gravitation would just be 9.81 newton per kilogram, right? That's what we're using there. Alrighty. If we were to look at the gravitational field strength at a point above the Earth's surface, then we could start to describe that using a different equation. Alrighty? But let's stop here and then we get into a point above the Earth's surface and then speak about circular orbits and apparent weightlessness.